All right, folks, welcome back to our conversation about conjugates and what that means for the ability of the solution to adjust its equilibrium for weak acids and weak bases. And when we have that conversation, we are inherently talking about buffered solutions. So let's think about what a buffered solution is. So if you're thinking about a buffer, like if you're buffing out your car, right, you're creating a barrier between your hands and the automobile so that you can like interact with the car to get a scratch out, right? Um, in a sense, we're going to be thinking in a similar context like that for our solutions that are buffered, in that there is some kind of like barrier or like protection that these solutions have against like external factors. So a buffered solution is a solution that resists any changes to its pH when you add either acid or base. And how is this possible? Like, how is it that I can have a solution that if I dump a bunch of strong acid or a bunch of strong base in, it doesn't change its pH? So the only way that a buffer solution could exist, like the only way that a solution can prevent its pH from changing, is if the solution has non-zero concentrations of conjugates species that exist in the solution. So for example, I would have a solution that had some non-zero concentrations of acid and its conjugate base, HA and A minus, that exist already in the solution. So pre-existing mixture of conjugates. So before, when we were talking about weak acids, we assumed that initially in the solution there was absolutely no A minus conjugate that was formed pre-dissociation. Here we are creating solutions that have weak acid and then are kind of like doped, right, with their weak base. So we're adding conjugate to a weak substance. So how does this work? Fundamentally, buffered solutions, meaning solutions that have conjugates present in non-zero relative concentrations, are acting on the principle of Le Chatelier's principle. So let's look at our weak acid beaker and let's see what happens to it according to Le Chatelier's principle if we add acid, if we add base, and how the presence of that conjugate ion A minus might be of use in terms of resisting any change to pH upon the addition of those acids and bases. Okay, so I'm going to look at a weak acid buffer solution. So in the middle here, this is going to be my original buffer that contains HA and its anion A minus. So I've got HA, which I know dissociates into H3O plus and A minus. And then I've also got A minus that pre-exists in the solution as well. So what were to happen if we were to add H3O plus versus if we were to add OH minus? All right. Now let's remember additionally what is going on with this conjugate base A minus. That conjugate base is undergoing its own dissociation. So like I've got HA with H2O undergoing its dissociation to create that. And then I also have A minus in the presence of H2O acting as its own weak base in its own right to create HA and OH minus. So I've also got some hydroxide that's in here. So that is what is in this beaker because we have pre-existing amounts of HA and A minus. So what does that mean is going to happen? Okay. Let's say I try to disturb this system by adding some amount of base. So if I add hydroxide, let's think about what in our beaker is going to react with that hydroxide. So if I now pop a bunch of hydroxide in here, all right. So I am going to neutralize my H3O plus. So thinking about what's going on in terms of the acid dissociation. If I start to take this product and decrease it by neutralizing with hydroxide, because I exist in an equilibrium, Le Chatelier's principle says that my reaction is going to drive itself forward to recreate that H3O plus. What about if we add acid? Okay, if we had acid, again, we're going to neutralize the hydroxide. And that hydroxide is only in solution because of A minus dissociating with water. To create HA and OH minus. So if I start decreasing the amount of hydroxide via neutralization, then my reaction is going to favor the production of HA product. And remember, HA is the thing that is responsible for putting H3O plus in solution. So it's another Le Chatelier, right? We have an increase in HA as a result of a Le Chatelier shift because we've decreased hydroxide. And now that we have HA back in solution, we can make freely more H3O plus to make up for the H3O plus that was neutralized away by adding, to make up for the hydroxide that was neutralized away, right? So like I've got production here that's going to shift right refavor the formation of hydroxide and also HA. So Le Chatelier's principle says that because we have both of these things present, these are going to, as a result of their dissociation products existing in the beaker, be able to be neutralized and then shift off their equilibrium to kind of like deflect that neutralization. So how do we quantify this, right? How do we talk about like the pH of a buffer solution? So the way that we have available to us to determine the pH of the buffer solution is by using the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation relates pH of a buffer solution to the relative concentrations of weak acid and its conjugate base that are present in solution. So the Henderson-Hasselbalch equation is as follows. pH is equal to pKa plus the log of concentration conjugate over concentration acid. So this is the Henderson-Hasselbalch equation. And where does this come from? So let's suppose that I've got some HA that is dissociating in water that is described by some Ka, which would be equal to H3O plus times concentration A minus over concentration HA at equilibrium. The Henderson-Hasselbalch equation is going to presume, that basically our X is small enough. In other words, this presumes that the concentration of HA and A minus that are present initially in the beaker, the system, the solution, are equal to the equilibrium concentrations. This allows us to say that Ka would be equal to concentration H3O plus, concentration A minus initial over concentration HA initial. And if I take the negative log of this equation, like why not? So I'll have the negative log of both sides. Okay, we just found for ourselves that the definition of pKa is the negative log of Ka. So this is the pKa. I can now apply some log rules. This becomes the negative log concentration H3O plus plus the negative log of A minus over HA. And since we are trying to obtain something that like gives us pH, which is what this value is here, I can add over this log term to both sides, and I get that pH is equal to pKa plus the log concentration A minus naught over HA naught. And the reason why I'm like highlighting the fact that we can use the small x approximation here is because this means that when we're talking about a buffer solution, we don't have to do any ice tables. We don't have to think about like what the actual equilibrium concentrations of molecular HA and its conjugate base A minus are. Like if I was told that a solution had, for example, over here, 1.0 molar HA and 0.85 molar A minus, I don't need to consider each of their respective weak dissociations, use an ice table to get their actual concentrations in the beaker, because the Henderson-Hasselbalch approximation says that in a buffered solution, these initial concentrations that would normally go in our ice table are approximately the same as our equilibrium concentrations, which is why we can put them into the Ka expression. So that's a nice little thing. It makes our life a bit easier. If you are a biologist or trying to obtain a biology degree, you are going to be dealing with buffers a lot. So let's practice how we think about the Henderson-Hasselbalch equation, how that allows us to think about like preparing a buffer solution. So here we have an example. A microbiologist wants to make a phosphate dihydrogen phosphate buffer. That's really common. Another one you'll see is carbonate buffers, right? And we want this buffer to have a pH of 6.43. What should the relative molarities of each ion be in solution to achieve this pH? The Ka of the dihydrogen phosphate is 6.3 times 10 to the negative 8. So there's a lot of information in here. Let's try to figure out like how we can piece it together. And the way that I want to start is I want to think about this value, the Ka. So this is implying that this undergoes a weak acid dissociation, right? If I'm given a Ka value for the dihydrogen phosphate ion, then that's the weak acid. All right. I also know my desired pH. So I know my pH. And now the goal is to figure out the relative molarities of phosphate, dihydrogen phosphate that need to be present in order for us to make a buffer that has this pH. So our goal is to get concentration of dihydrogen phosphate and the concentration of phosphate that are needed to make the solution. I believe it should be HPO4 2 minus. There we go. All right. Anytime we hear the word buffer, we should be thinking about the Henderson-Hasselbalch equation. So let's write the Henderson-Hasselbalch equation. This says that pH is equal to the pKa of the weak acid plus the log of the proportion of concentrations of the added amount of conjugate base, A minus, compared to the amount of acid, HA, where again, we are assuming that these are their original concentrations, like as described, as prepared. I don't need to do any kind of equilibrium analysis to determine like what the actual quantities of these are in the beaker, because those will be very, very, very similar to our initial ones. So we're kind of like presuming a small x approximation here. So let's see here. What was I given that relates to Ka? I was given pK, I was given Ka, so this relates to pKa. So I need to find my pKa by taking the negative log of my Ka. So that's my 6.3 times 10 to the negative 8. That is equal to pH. I have a desired pH here for the microbiologist, something slightly less than neutral. Plus the log of the concentration of A minus. So what is A minus here? This is going to be the phosphate ion, because we were given the Ka for the hydrogen, dihydrogen phosphate. So that's the weak acid whose Ka is known. So its conjugate base must be the phosphate. And our goal is to figure out the relative molarities, meaning I need to know what this fraction is here, right? That's a relationship. So that is my goal, to figure out what the value is inside this log that makes the rest of this true. So let's find our pKa. So that is going to be negative log base 10 of our Ka, which is 6.3, times 10 to the negative 8. So I have 6.43 pH is equal to 7.20067 plus log of, let's just go ahead and call this x. All right, I need to solve for what's inside the log. So let's first isolate the log term. So 6.43 minus our 7.2006. So when I subtract this over, I get negative 0.757, carrying a couple digits there. That's equal to log of x And now to do an inverse of a log base 10, I need to raise each side of my equation here as an exponent, with the base of the exponent being 10. So I'm going to do 10 to the both sides, so 10 to the negative 0.757659 is equal to 10 to the log of x. All right, so 10 to the negative 0.757. On the left-hand side, this gives me 0.174 sub 7 is equal to x. So what is this saying? This is saying that my concentration of phosphate ion over my concentration of weak acid dihydrogen phosphate is 0.17 with rounding 5. Another way to think about this is the concentration of phosphate has to be equal to 0.175 times the concentration of dihydrogen phosphate. Or another way to think about this in terms of a percentage, the concentration of phosphate needed is 17.5%, whatever the concentration of dihydrogen phosphate is in solution. So from there, with that information, the microbiologist could say, okay, well, I've got some like 0.5 molar dihydrogen phosphate solution. How much sodium phosphate, aka source of phosphate, would I need to dissolve so that that is now 17.5, that 0.500 molar. So we always prepare a buffer by having some weak species and then adding its conjugate to it. Now, remember, buffers are fundamentally things that resist changes to pH. However, these are not things that can resist changes to pH indefinitely. Meaning, like this Le Chatelier process of shifting right, shifting left to accommodate the fact that each of these things have been neutralized. This is something that can be exhausted, right? Like eventually you're gonna run out of acid particles. Like say I keep neutralizing all of these acids, that's gonna drive all of these HAs forward. And eventually I'm gonna run out of HAs to like drive forward to make H3O plus to compensate for the loss, right? Same deal here. If I neutralize all of these hydroxides, that is going to cause like continual shifts forward. That's going to deplete A minus until it's completely gone from solution. So when describing like the capacity or the ability of a solution to resist changes to pH, it is like able to hold up against these changes to pH over some range. And we call that the buffering capacity. So buffered solutions can only resist changes to pH as long as sufficient amounts of HA and A minus remain in solution. Because once HA runs out, then what's going to happen is if I drop this all to 0, because I have neutralized too much of this, so all of this was consumed in driving the reaction forward to counter the addition of hydroxide, then I no longer have a solution that exists with both acid and conjugate. So I'm no longer a buffer. Same deal if we think about the weak acid, A minus, sorry, the weak base, the weak conjugate base. So as this gets neutralized, our hydroxide gets neutralized, then we are going to eventually deplete A minus. So this is also consumed in driving reaction forward to counter H3O plus, where again, this hydroxide is neutralizing H3O plus product. And here, acid is neutralizing our hydroxide product. And if we no longer have HA and A minus because they're consumed, then we are no longer a buffer. So once these are all consumed, we can no longer be a buffer because we've exhausted our ability to shift according to Le Chatelier's principle. I've eventually run out of the source of the thing that made my acid that could be neutralized by the base, etc. Like remake my acid as needed. So if all the conjugates are gone, cannot be a buffer because the conjugates are what's responsible for allowing that H3O plus or that hydroxide to exist in solution. They are the reactants that are shifting forward when the product is removed. So shifting forward when the product is removed, and it can only shift forward until all of that reactant is consumed. So buffers are not buffers forever. However, we can define the buffering capacity of a buffer. In general, the rule of thumb is as long as the concentration of a conjugate is at least 10% the concentration of the original weak species that conjugate came from, we will remain a buffer. And an even easier rule of thumb is that like the buffering capacity or the range at which we can expect to still be able to resist pHs is whatever the pKa of our weak acid was, plus or minus 1. So that will tell us like the range at which our pHs will kind of remain constant. So for example, like if I were to think about I think we did, what do you do here? Yeah, the dihydrogen phosphate. The pKa here was 7.2. So the buffer capacity of a buffer containing dihydrogen phosphate and phosphate would be like 6.2 and 8.2. So it could handle slightly basic conditions. So pKa plus or minus 1 is about how we know over which range we can expect our buffer to still be a buffer. All right. In our next video, we're going to go over how this all relates to a weak base, right? Because if you notice, going back to our Henderson-Hasselbalch equation, this is in terms of pH. So that presumes it's a solution with like acid, right? H3O plus in it, hydronium. It also has a pH, which presumes we're looking at a weak acid dissociation. And it's a proportion of conjugate substances, but it's the weak acid and its conjugate base. So this is the Henderson-Hasselbalch equation expressed in terms of like what's going on if we are in acidic solution. And as you've seen in our titrations labs, that's not the only kind of titration that can exist, right? We can look at what happens to the pH of something that is a basic buffer. So next video will be kind of like a reimagining of the Henderson-Hasselbalch equation according to a weak base, so a Kb and a pKb. And then from there, we will begin to talk about titrations, titration curves, why they look the way that they do, and really explaining the chemistry behind what we observe when we graphically look at how pH is changing as we add more and more and more reactant, our titrant, to our reaction flask. So I'll see you in our next video.